Let's get started. Let's take roll. Okay. Amo?
Here.
Bessie? Here. Bishop?
Here.
Bragg?
Here.
Audio? Chestnut? Code? Burlinson? Gerard? Green? Kennedy? Leonard? Mohammed Boy? Small? Here, right? Solomon?
Here.
And Swiss that is here. All right. So we're going to continue our discussion of chapter 5. And we're going to look at another law. Believe it or not, we have more laws concerning the behavior of gases. And this law is a law which deals with gases involved in a reaction. It's called the law of combining volumes, right? And basically what this law says, when gases are measured at the same temperature and pressure, are allowed to react, the volumes of the gases, reactants, and products are in small whole number ratios. So, if you're looking at, for example, the reaction between hydrogen and oxygen to form water, what you'll find is that for every 2 liters of hydrogen that reacts, it will react with 1 liter of oxygen. And why? Well, that is of course based on the balanced equation, which I'm going to write here. And that equation, of course, is H2 plus O2 to give H2O. And to balance this, we need a 2 here and a 2 here, right? So basically, if you focus on the relationship between the hydrogen and oxygen, you see that there's a 2 mole to 1 mole ratio between H2 and H2. Well, it turns out that if the temperature and pressure of all the gases are the same, then the mole ratios established by the coefficients will also be equal to the volume ratios established by the coefficient, right? So in other words, 2 liters of hydrogen will react with 1 liter of oxygen, right? Assuming that these are all gases, including the H2 on this side, which means that 2 liters of water vapor will be produced as well, all right? So that's basically how those small whole number ratios are arrived at. It's based on the coefficients of the different gases in the balanced equation, all right? Here's another example. At a given temperature and pressure, 6 liters of hydrogen will react with 2 liters of nitrogen to form 4 liters of ammonia. And again, this is based on the balanced equation, which would be N2 plus H2 to give ammonia, which is NH3. And to balance this, let me give up some space here. And to balance this, H3 here, to balance this, we're going to need a 3 here, 1 here, and a 2 here. So in this case, it's a 3 to 1 to 2 ratio, which is the same thing effectively as okay, I did this wrong. This should be 3 here. This should be 3 here, and this should be 2 here. All right. So this is a 2 to 3 to 1 ratio, which basically is the same thing effectively as a which is effectively the same thing as a 2 to 6 to 4 ratio in terms of moles and also in terms of volume, provided again that the temperature and pressure are the same for all the gases, all right? So that's basically what the law of combining volumes is all about. Okay, so that's it, right? As far as this law is concerned, and as stated here in the last bullet point right here, we do not even need to know the actual conditions. In other words, we don't even need to know the temperature and the pressure of the gases in order to establish that relationship, as long as they're the same. The temperature and pressure of all the gases must be the same in order for this law to work, all right? So this is just a pictorial description of the same law. And again, this is involving the reaction between hydrogen and oxygen to form water. And again, these are two gases, right? And basically these containers basically have the same volumes. These are two volume units of hydrogen, one volume unit of oxygen, and that would give you two volume units of water, all right? And that's it. That's just basically what is established by the coefficients in the balance equation. Basically, the volume ratio will be the same as the ratios of the coefficients of the different substances involved, if they are gases at the same temperature and pressure, all right? So that's basically what that is all about, all right? Now, using that law, we can answer questions such as the one that you see here on the screen. It says here, how many liters of oxygen are consumed for every 10.0 liters of carbon dioxide produced in the combustion of liquid pentane, and it gives you the formula for liquid pentane, if all the volumes are measured at SDP. So what would be the very first thing you would do in order to answer this question? I'm sorry?
Right, the reaction comes.
Or more specifically, the balance equation. So what would be the reactants in this equation based on the information provided in the question? I'm sorry? Water and oxygen. Well, the oxygen part you're right about, but water would not be a reactant. Water would be a product.
Degradation.
I'm sorry? Pentane, that would be one of the reactants. Right? Plus oxygen, as she said, and water would be one of the products. And what would be the other product? Based on the information provided in the question. CO2, exactly. And then we have to balance it. So this is a gas. This is a gas. And they didn't specify about the water, so water could be a liquid or gas. Not important, anyway. Okay, so now we have to balance it. So how would we go about balancing this equation? Well, you all should know how to do this by now. The 5 in front of the CO2. Yes? No? 6 in front of the H2O. Anything else? And then 8 in front of the O2, and now the equation is balanced, right? So you have to do that first before you can do anything else, right? So the question is asking how many liters of oxygen. This is what the question is asking for. If for every 10.0 liters are consumed, I'm sorry, for every 10.0 liters of carbon dioxide. So you're given 10.0 liters of CO2, and the question is asking for the liters of O2, right? So start off with what we're given. So the question now becomes, what do we multiply this by in order to get the volume of O2? And the answer lies in the coefficient, right? We have 8 liters of oxygen that will react to produce 5 liters of carbon dioxide based on this equation. So I would put 5 liters of CO2 here and 8 liters of oxygen here. And the reason why I can do that is because they're all measured at the same temperature and pressure, right? So the volume ratios will be the same as the mole ratio. And then all we have to do is the math. So for the look of things, the answer here will be 16.0 liters of oxygen, right? This will cancel out with that, and therefore that would be the answer, right? Any questions about this? Any questions? Questions? Any questions out there in Zoom? Okay, so we move on to the next slide. Okay, so now we're going to look at situations where the temperature and pressure of all the gases are not necessarily the same, right? So that will complicate things a bit when you're doing calculations like what we just did. So we're going to look at more specifically what we call gas stoichiometry. In fact, the example that we looked at is an example of gas stoichiometry. If you remember what stoichiometry, that term means, stoichiometry is that area of chemistry which deals with the quantitative relationships between different substances involved in a chemical reaction. So we just saw an example of that in the previous example, and now we're going to get into something a bit more complex, because you can end up in a situation where the pressures of the gases involved are not the same, or the temperatures of the gases are not the same, and therefore it is not as simple and straightforward as the example that I gave you below. So we need to remind ourselves of certain things when it comes to stoichiometry generally, right? And that is that we have to use some of the concepts and methods that we were exposed to in an earlier chapter, chapter 3, right? Plus, we have to combine that concept with what we learned concerning the behavior of gases as described by the ideal gas equation, all right? So, if you recall, back in chapter 3, when it comes to determining, let's say, the amount of product given a certain amount of reactant or vice versa, it basically comes down to the mole ratio, right? The mole ratio between the different substances, the one that you're given, and in order to work to the one that you're trying to find some value of, mole, mass, whatever, then you have to use the mole ratio as given in the balanced equation, which again underscores the importance of having a balanced equation to begin with, right? If the equation is not balanced, then more than likely your resulting calculations will be erroneous, all right? So as stated here, let's say A is a gas, so we're dealing with gaseous reactions or reactions involving gases. Let's say you're given information like the pressure, volume, and temperature. The first thing you'd have to do is find the number of moles of that gas, right? And then using the mole ratio established by the balanced equation, you can determine the moles of any other substance, again, maybe a gas, right? So you use the mole ratio multiplied by the moles of the initial substance to get the moles of the other substance, let's call it substance B. And then again, based on how the question is worded, you may be asked to determine, let's say, the volume or the temperature, whatever, and that's where the ideal gas equation will come into play, all right? So that's basically what is involved in the vast majority of gas stoichiometric type problems. And I think the next slide is an example of that, indeed. So they gave you this equation here, right? Balanced, fortunately, for us. And then it says, what volume? So it's asking for the volume of the gas, right? Measured at 25 degrees, which is the temperature which we have to convert to Kelvin. So that's 298 Kelvin. And the pressure here, right? 0.90 atmospheres is produced by the decomposition of this much sodium azide, which is this compound here, right? So the first thing I would do is I would start off with the 62.5 grams of the sodium azide. And I will convert that to moles, right? So I'm going to put 1 mole of NaN3 here, and I would have to calculate the molar mass of the sodium azide. The sodium is 22.99 plus 3 times nitrogen, which is 14.01. And according to my calculation, this works out to be equal to 65.02. 65.02 grams of sodium azide. And again, I keep saying, folks, do these calculations with me because I could be wrong. So please check behind what I've done and correct me if necessary, all right? But so far, this is what I have, right? So the next step in this, in solving this problem is that I will look at the mole ratio between the sodium azide and the nitrogen, because the question is asking ultimately for the volume of nitrogen. But so far, you'll be able to determine the mole of nitrogen based on the mole ratio between the nitrogen and the sodium azide as described in this equation, right? So the way I would represent that here is that I'll put 3 moles of nitrogen, N2, above as a numerator, and 2 moles of sodium azide below as the denominator, all right? So this will cancel out with this, and then I would do the calculation, 62.5 divided by 65.02 times 3 divided by 2. So according to my calculations, this is equal to 1.44 moles of nitrogen. But the question is asking for the volume of nitrogen, all right? So what I would do is use this equation, the ideal gas equation, remember is PV is equal to nRT. What I'm trying to find is the V. So therefore the V would be equal to nRT over P as a result of the rearrangement of that equation. And I'll plug in a number. Now N is what we just calculated here, which is the number of moles, which is 1.44 moles times R, which is always 0.0821 liters atmospheres over mole Kelvin, times the temperature, which is 298 Kelvin, and then we would divide all of this by the pressure, which is 0.980 atmospheres. And that's basically the setup in terms of unit cancellations. This is what will happen. Atmospheres cancel out. So the only unit remaining will be liters. So let's do this calculation. 1.44 times 0.0821 times 298, and then divide that by 0.980. And according to my calculation, this works out to be 35.9, when rounded off to 366, 35.9 liters. And that would be the answer to this question. All right? Any questions about this example? Any questions? Any questions? Okay, so let's see here. Okay, so before we move on to Dalton's law of partial pressure, let me go back to the assignment and so let me go here. Yes, sir.
Do you have any more copies of Sunday File?
I don't think so, no.
Thank you.
All right. Okay, so let's go to assignment 5. Download. Okay, so based on what we have covered so far, we did do question 7, right?
Correct.
Okay, so let me see here. Okay, there are several questions we can look at. We just really wanted to let's see here. I have to jump maybe 1 or 2 questions. Okay, all right. I'll decide as we go along which question we're going to look at. Okay, so I'm going to start with question number 8. It says calculate the pressure of let's do it. Okay, so it says calculate the partial pressure of each component in a mixture of gases containing 3.50 grams of nitrogen, 2.15 grams of hydrogen, 5.27 grams of ammonia, if the temperature is 25 degrees and the volume of the mixture is 1.00 liters. Now, this is dealing with a gaseous mixture, which I will admit we have not dealt with that yet, because that would be the next topic. But you still should be able to do this question, because basically what this question is asking for is the pressure of each gas in the mixture, right? So the equation you're going to use is the equation that we have been using all along, which is PV is equal to nRT, right? What the question is asking for is P for each gas, which would be equal to N times RT over V. So basically, you'll be applying this particular formula for each gas, nitrogen, hydrogen, and ammonia in the mixture, right? They gave you the temperature, which again, you have to convert to Kelvin. So that's 298 Kelvin. And they gave you the volume, right? So that's the volume, all right? So basically, you have the temperature, you have the volume, you have R. The only thing you need to calculate for each gas is the number of moles, right? So if we do that for nitrogen, that will equal to the number of moles of nitrogen. Now, how do we get the number of moles? They gave us the mass in grams, 3.50 grams, and we have to convert that to moles, right? So in the case of ammonia, the molar mass, 14.41 plus 3 times 1.008 And according to my calculation, this is equal to 17.03 grams of ammonia. No, I'm sorry, nitrogen. My bad. So that should be 2 times. Oops. That should be 2 times 14.01, which is 28.02. Okay, so 28.02, right? So this will give you the moles, and then we multiply by R, which is always 0.0821 liters atmospheres, oops, over mole Kelvin, times the temperature, which is 298 Kelvin, multiply by, and then divide all of that by the volume, which is 1.00 liters. So that is for nitrogen, so 3.5 divided by 28.02 times 0.0821 times 298 divided by 1. And when rounded off to 3 sig figs, the answer I got is 3.01. And the units will be atmospheres because the liter units go, the Kelvin goes, the mole goes, and this gram here will go with this gram. So the only unit remaining would be atmospheres, right? And if you understand that, then you should be able to calculate the pressures for the others as well. The only difference is that here, the mass will be different, and here the molar mass will be different, right? But it's the same arrangement, same calculation. So I'm gonna leave you guys to do that on your own. If you have any problems, please let me know. Any questions about this? Any questions? Any questions? Okay, let me clear this. Go down. And then, okay, now this one is interesting. I want you to read it carefully, or let's read it together so you understand what's happening here. You have a container A. It has a volume of 1.23 decimeters cubed and contains a gas under 3.25 atmospheres of pressure. Then you have container B with a volume of 0.93 decimeters cubed and it contains a gas under 2.82 atmosphere pressure. And then you have a container C, has its own volume of 1.42 decimeters cubed, and the pressure of that gas is 1.21 atmospheres. It says if all these gases were put into a fourth container B, the volume of which is 1.51 decimeters cubed, what is the pressure of the gases in container B? So how would you, well, let me ask you this. What law do you think comes into play in this particular question? You can feel free to look in your notes or the PowerPoint or whatever. We have dealt with several laws, right? So which specific law? Oh, wait a minute, I just realized something. We have the Dalton's law of partial pressure, right?
No, that was the next.
Okay, all right. Scratch this question. I just realized. There are 2 laws that are needed, one of which you have met before, but the other one we haven't met before. So we can't do that one yet. All right, sorry about that. Sorry about that. We're gonna come to it. Let me see, number 10. Okay, can't do number 10 either, for the same reason. Number 11, can't do number 11 either. Okay, number 12. Let's do number 12. Number 12 is of the type that we just looked at in the PowerPoint, right? They gave you the balance equation, and the question is asking how many liters of ammonia at 850 degrees and 5.00 atmospheres are required to react with 1.00 mole of oxygen. All right. So this is very similar to the example that we worked in the PowerPoint, right? So I want to hear what you have to say about this. How would you go about solving this problem? They gave you the equation, balanced. They gave you the temperature. They gave you the pressure of ammonia. All right. And they gave you 1 mole of oxygen. So you have 2 reactants you're dealing with. One of which is oxygen, the other one is ammonia. So how would you go about tackling this problem? Okay, so the volume, let's write that formula because yes, you're going to need that formula. So let's write that formula down. The volume is equal to nRT over P. Okay, so next step. Under what? I didn't hear that.
The NH3 though.
Ammonia, what about it? Well, I don't think you have what it takes to convert it to moles, because you don't know what the mass is. Well, you can convert it to moles, or you can obtain moles. How would you do that? I'm sorry? Okay, so you're going to start off with 1.00 moles of O2, and what do you do with that? Multiply by the mole ratio. So what's the mole ratio? In other words, what goes up top here as a numerator and what goes down here as a denominator? 4 moles of ammonia over 5 moles of O2, right? So that gives you the moles. So that works out to be equal to 0.800 moles of ammonia. Okay, so now that we have the moles of ammonia, what will be the next step? Oh, yes, indeed. So what's 850 plus 273? So I got 1123 Kelvin, right? Okay, that's important too. Okay, what next? Okay, into this equation, right? So volume is equal to N, which we just calculated, 0.800 moles times R, which is 0.0821 liters atmospheres over mole Kelvin, times the temperature, which is 1123 Kelvin, all divided by the pressure, which is, what's the pressure? 5.00 atmospheres, right? So let's do the number crunching. 0.8 times 0.0821 times 1123, and then divide by 5. And according to my calculations, when rounded up to 3/6 figs, I got the answer as 14.8, and the units would be liters, because the Kelvin will cancel out here and here, the moles will cancel out there and there, atmospheres cancels. So therefore, you're going to be left with 14.8 liters, and that would be the answer for the A part of question number 12. All right? Any questions about that? Questions? Okay, is it okay for me to clear this? Yes, no, maybe so? All right, let me clear it. And let me scroll down to part B. Same equation, but this time the question is asking for the moles of water. Let me scroll this all the way down. So this time, the question is asking for the moles of water, right? Now they gave you the volume of ammonia, they gave you its pressure, and they gave you its temperature in Kelvin, right? So again, you're going to use the PV is equal to nRT equation. So let me hear what you have to say about this one. How would you solve this one? N is equal to? Okay. So this would be the number of moles of ammonia, right? So the pressure is 5.00 atmospheres times the volume, which is 450 liters, divided by R, which is 0.0821 liters atmospheres over mole Kelvin, times the temperature, which is 295 Kelvin. So let's see what that gives. 5 times 450 equals that, divided by 0.0821, divided by 295. And according to my calculations, I got 92.9 moles. All right. So remember now, this is the moles of NH3. Now, what the question is asking for is the moles of H2O. So according to the equation, let me back up, scroll back up here. According to the equation, the mole ratio between the water and the ammonia is 6 moles of water for every mole of ammonia, right? I'm sorry, 6 moles of water for 4 moles of ammonia. 6.4, all right? So what I would do is start off with what we just calculated, which is the 92.9 NH3. And I'll multiply this by 6 moles of H2O for every 4 moles of NH3. And let's see what that gives. 92.9 times 6 divided by 4. So according to my calculations, when rounded off to 3/6, the answer is 139 moles of H2O. And that would be the answer that the question is asking. All right? Okay, any question about this one? Questions? Okay, I don't think there's any other question we can do for now. Let me just scroll down and check this here. Okay, right, so you won't be able to do the other, so let me go back to the PowerPoint after clearing this. Okay, so now we're going to get into gaseous mixtures. And there's another law put forward by Dalton. Dalton's law of partial pressures. Dalton, by the way, was the same person who came up with the atomic theory of matter. So this law has to do with mixture of gases, right? So far in our discussions, we have been dealing with only like one gas and you know, the different things, factors that affects it and so on. So here we're dealing with a mixture of gases, right? And what Dalton's law is saying is that if you have a mixture of gases, the total pressure of that gaseous mixture is equal to the sum of the individual partial pressures of the gases in the mixture, right? So basically what his law is suggesting is that each gas is acting independently in terms of the pressure it exerts, right? So the mathematical way of expressing this law is right here. P total, which is the total pressure of the gas mixture, is equal to P1 plus P2 plus P3, and so on. Whatever the number of gases in the mixture, basically adding them up in terms of their pressure will give you the total pressure of the mixture, all right? Now, the term partial pressure, of course, is referring to the pressure that a gas would have exerted by itself if it was the only gas present in a container, right? So we can basically write down different equations for each gaseous component in the mixture. So for gas 1, the pressure of that gas will be equal to N1, the number of moles of that gas, times RT over V, and we can write down similar expressions for gas 2, gas 3, and so on, right? Now let's look at this in more detail. I'm going to get out of this here. And go to Word. So what I'm going to do now is look at, okay, so the pressure of each gas will be equal to nRT over V, right? Now, basically, gases in a mixture will basically have the same volume because they're in the same container, right? They will also have the same temperature, again, because they're in the same container, right? So T and V would be the same for all the gases. So the only difference possibly for the different gases would be the number of moles, and that would result in the pressures being different. So for gas 1, P1 is equal to N1 RT over V, and for gas 2, P2 is equal to N2 RT over V, and so on and so forth, right? So PT will be equal to P1 plus P2 plus P3 plus, and so on to the nth gas, Pn. So that will be equal to N1 RT over V plus N2 RT over V plus N3 RT over V plus, and so on to N RT over V, all right? And then if we factor out RT over V, that's a common factor that we can take out of each of these, then you're going to end up with RT over V times N1 plus N2 plus N3 plus and so on to Nn, right? And we can say that this total here, I'm gonna write it here, N1 plus N2 plus N3 plus and so on to Nn, we can say that is equal to the total number of moles Nt, right? So I'm just gonna put Nt right here, and the resulting equation would be Nt times RT over P over V, I'm sorry, right? So basically, what we're saying here is that the total pressure of the gaseous mixture will be equal to the total moles of all the gases in the mixture times RT divided by V, right? So basically, this is a way of calculating the total pressure. All you have to do is add up the moles of the gases in the mixture and then multiply by RT divided by V, and that will give you the total pressure, all right? So, going back to the PowerPoint, I think there's an example in the next slide, which says a 1.00 liter sample of dry air at 25 degrees Celsius, and it gives you the moles of each of them, 0.0319 moles of nitrogen, 0.00856 moles of oxygen, 0.000381 moles of argon, and 0.00002 moles of carbon dioxide. So the question is asking for you to calculate the partial pressure of all the gases in the mixture and the total pressure of the gaseous mixture, right? So basically, you're going to use the same equation that we used before. P is equal to nRT over V. So in the case of nitrogen, that would be equal to the number of moles of nitrogen, which is 0.0319 moles, times R, which is 0.0821 liters, atmospheres over mole Kelvin, times the temperature, 25 degrees, which you have to convert to Kelvin again, so that's 298 Kelvin. And then we divide all of that by the volume, which is 1.00 liters. And basically, it's the same setup for the other gases. So for oxygen, the only difference is the moles, in which case, in the case of oxygen, it's 0.00856 moles times 0.0821 liters atmospheres over mole Kelvin multiplied by 298 Kelvin, all divided by 1.00 liters, and then we do the same calculation for argon. The moles for that would be 0.000381 moles times 0.0821 liters atmospheres over mole Kelvin times 298 Kelvin, all divided by 1.00 liters. And then we do the last one, which I hope I can fit somewhere down here. Pressure of CO2. That would be equal to the mole of that would be 0.000, how many zero? 4 zeros. Then 2 moles times R 0.0821 liters atmospheres over mole Kelvin times 298 Kelvin divided by 1.00 atmospheres. Okay, so we have to work out each of these. So for the first one, 0.0319 times 0.0821 times 298. And according to my calculation, this works out to be 0.78. Let's say 360, so 0.780 atmospheres. In the case of oxygen, it is 0.00856 times 0.0821 times 298 divided by 1. 0.209 atmospheres. And then for this one, it is 0.00381 times 0.0821 times 298 divided by 1. So this is 0. How many seconds? 3 seconds, so 0.0932 atmospheres. And then for the last one, which is carbon dioxide, it's 0.0002 times 0.0821 times 298, and then divide by 1. So this would be a very small number, which is 5 times 10 to the minus 3 atmospheres. Let me do this one again. Maybe I did something wrong. I have a sneaking suspicion that I made a mistake.
I think you skipped a 0.
What's that?
Maybe missed a 0. 4 zeros?
Oh, I did? I kind of suspected I did something wrong. Times 0.0821 times 298 divided by 1. Yes, it should be minus 4 here, minus 3. Okay, and then so we have answered the first part. Second part is to get the total pressure, which is very simple. All we have to do is add all these up. So we're gonna add 0.780 plus 0.209 plus 0.0932 plus 5 times 10 to the minus 4. And we have to round up to 3 decimal places, so the answer here becomes 1.08 atmospheres. And that's how that is done. Any questions? Any question about this example? Okay, let me scroll down here. Okay, so this is just a pictorial illustration of what we just talked about. The fact that, basically, to get the total pressure from mixture of gases, you have to take into account the pressure of each gas, add them up, and that's where you get the total pressure. So in this illustration, we have a container here which contains hydrogen. They gave you the number of moles and they gave you the pressure, right? And the volume and temperature is given as well, right? At the same volume and temperature, there's another gas in this container. This is the mole value, this is the pressure value, right? So when you mix them together, under the same conditions of temperature and volume, basically the total pressure, 10.1, would be the sum of the individual pressure, which is 2.9 plus 7.2, right? Of course, the total mole value would be the same result when you add the moles of each of them. So 1.5 plus 0.60 gives you 2.10 moles, right? So that's basically how the Dalton's law of partial pressure works. So there's a question I think that's here, and the question is, what would be the total pressure? Because now you should see, before I get into the question, now you should see that there is a proportional relationship between the moles of the gas, regardless of what the gases are, but the total moles of the gas is proportional to the total pressure. So here's a question being asked. What would happen in terms of the total pressure if you add a further 0.9 moles of nitrogen into this mixture here, right? So basically, we know that there is a direct relationship between the number of moles and the pressure of the gas. So the number of moles is directly proportional to the pressure. Total number of moles equal to the total, or directly proportional to the total pressure, right? So if we start off with here, what should I do? So I'm just asking for the total pressure, right? So the total pressure here is 10.1 moles. If we divide that by 2.1 moles, I'm sorry, the total pressure is 10.1 atmospheres. Using the wrong unit here. Come on. Okay. So 10.1 atmospheres divided by 2.10 moles is equal to a constant, right? And that would be equal to, let me do this over here. 10.1 atmospheres divided by 2.10 moles, right? And if we increase the number of moles to 2.10 plus 0.9, so that would be equal to 3.0 moles. 3.00 moles, then what would be the new total pressure here? Right? But that would be very easy. All we have to do is, let me do it up here. PT, total pressure, the new one would be equal to 3.00 moles times 10.1 atmospheres divided by 2.10 moles, whatever that gives. So that would be equal to 3 times 10.1 divided by 2.1, and according to my calculations, that will be equal to 14.4 atmospheres. All right, so that's how you can easily calculate the pressure based on the moles of the gases in a container because of the proportional relationship between the moles and the pressure. All right, which makes sense based on the ideal gas law. Remember, the ideal gas law is PV is equal to nRT, right? So if V is constant, R is constant always, and temperature is constant, then the pressure will be directly proportional to the number of moles. So that's how you can do calculations of this type. Okay, so let me talk about mole fraction and then we'll get into some more problems in the assignment. So mole fraction, this term refers to a way of expressing, excuse me, the concentration of one component in a mixture of different components. And it can be applied to pretty much any type of mixture. However, in this chapter, since we're dealing with gases, we're going to apply the concept, the mole fraction concept to gases, right? So the definition of mole fraction is what you see here on the screen. It is the, so if we're asking about the mole fraction of one component in a mixture, then by definition, that's equal to the moles of that component divided by the sum of the moles of all the components in that mixture, right? So that is by definition the mole fraction. And because you're dividing mole by mole, that means that the mole fraction will have no units, all right? Because the units will cancel out. If you're dividing mole by mole, then the mole units will cancel out, so the mole fraction has no unit. Another thing too we need to say about the mole fraction is that the mole fraction can only range from a value of 0, which means that there is none of that component in the mixture, to 1, which means that it's the only component, right? So the mole fraction can only range from 0 to 1, all right? So that's the mole fraction. And because of the fact that the moles is directly proportional to the pressure as we saw before, based on the ideal gas equation, if the volume and the temperature are constant, then another way of expressing the mole fraction is by looking at the ratio of the pressure of one component, of that component in the mixture, divided by the total pressure of all the components in the mixture. So this is the definition of the mole fraction, but this is another way of calculating it based on the pressure of the gases in the mixture, all right? So this is a way of calculating it, and we can rewrite it as this right here. So in other words, if you know the total pressure of the gaseous mixture, and if you know the mole fraction of one of the components in the mixture, then you can calculate the pressure of that component, all right? Okay, so that's the mole fraction. That's the introduction to the mole fraction, all right? So let's look at this example. It says the main components of dry air by volume are, and it gives you the different numbers percentage-wise for nitrogen, oxygen, argon, and the carbon dioxide. So the question is asking, what is the partial pressure of each gas in a sample of air at 1.00 atmospheres? Now, they said that the percentages by volume are given, right? Those percentages are basically the same as the percentages by pressure, right? Assuming that the number of moles and so on are fixed. Let me just go back here and check something. Okay, so basically what you're gonna do is this. Define the partial pressure of each component. Right, you basically, so let's say for nitrogen, you're gonna take the percentage for nitrogen, which would be 78.08%, which would be the same thing as 0.7808. And then you multiply that by the total pressure, which is 1.0000 atmospheres. And the answer is going to be 0.7808 atmospheres, right? And that's basically it. You can do the same thing for argon, the same type of calculation for oxygen, the same type of calculation for what's the other gas? Carbon dioxide, right? And it's basically the same thing, right? So I'm gonna leave that for you to do on your own, but basically that's it. You multiply the percentage by volume by the total pressure in atmospheres, and that will give you the pressure of the separate gases individually. All right, so I'll leave you to do that. If you have any problems with that, please let me know. Okay, and okay, let's do this one and then we'll get into the problem. So when it comes to certain gases that are made in the lab, and it depends on the gas. One way of conveniently collecting the gas is by collecting it over water. Now, this will only work if the gas is very insoluble in water, right? So gases like oxygen, nitrogen, hydrocarbon gases like methane, propane, and so on. Those gases can be collected using the method of collecting the gas over water, right? If you're talking about gases that are water soluble, like ammonia or hydrogen chloride, won't work because the gases would simply dissolve in the water, right? So what is being shown here is the setup, right? What you do is that you have a trough filled with water, okay? And then you have a jar, which is also filled with water, and then you invert that jar into the water, and then you have a tube leading from the vessel where the reaction produces the gas is occurring. The gas is generated, in this case, the example used here is oxygen. So the oxygen is generated in a vessel and is led by this tube into the jar. And because oxygen is not soluble in water appreciably, then what will happen is that oxygen will start accumulating above the water surface right here. And then that pressure, as the oxygen accumulates, will force the water down. And what we try to do when we have this setup is that we collect enough oxygen such that the water level here inside the jar is at the same level as outside the jar. And the reason why we try to have that arrangement is because if the water level inside here is the same as outside, what that means is that the pressure of the gas inside here would be equal to the barometric pressure of the gas exerted on the surface of the water outside the jar. Based on that, we can determine the pressure of the gas that is collected inside the jar. Now, the thing about this that you need to recognize is that the gas that is collected is saturated with water vapor. So there are two gases that will be here. One will be oxygen and the other one will be water vapor, right? So basically the total pressure of the gaseous mixture will be equal to, right, it's down here. The total pressure of the gaseous mixture will be equal to the water vapor pressure and the pressure of the gas, which in this case is oxygen, all right? So basically, if we know the total pressure, of course, we can do that using the barometer, if we have that in the lab. And if you know the vapor pressure of the water, which you can determine because there are actual tables that are produced, which gives you the vapor pressure of water at different temperatures, right? So if you know these two items, then you can easily find the pressure of the oxygen calculated. So the pressure of the gas collected would be equal to the difference between the total vapor pressure, the total pressure and the vapor pressure, which would be the same as the barometric pressure. So this would be equal to the barometric pressure because the water levels are the same inside and outside the jar. So basically the difference between the barometric pressure and the water vapor pressure will give you the pressure of the gas, right? And I think the next slide has an example of a question which deals with this situation. Okay, I'm gonna need some space here. Let me see if I can enable this a bit. That should be enough space. Okay, so the question says hydrogen is collected over water. And it gives you the balance equation for the reaction, which produces the hydrogen. And it gives you also the temperature, which again you have to convert to Kelvin. So that's 293 Kelvin. And it gives you the pressure in torr. And the question is asking what volume of the wet gas, which is the gas that is collected over water, will be collected in a reaction of 1.50 grams of aluminum with excess hydrochloric acid. All right, so how would we do this? Well, what I will do first is start off with the 1.50 grams of aluminum. And I will convert that to moles. So I'm going to have 1 mole of aluminum above. And the molar mass of aluminum is 26.96 grams of aluminum. And then I'll look at the mole ratio between the hydrogen and the aluminum, and that's a 3:2 mole ratio. So I'm going to put 3 moles of H2 above, 2 moles of aluminum below, and I will work that out. So 1.5 divided by 26.9, 6, and then multiply by 3, divided by 2. So according to my calculations, this works out to be equal to 0.0835, roll it out to 3 sig figs, and this will be moles of H2, all right? So that's the moles of H2. Now this is the H2 that is collected, and what the question is asking for is the volume. The volume will be equal to the number of moles of H2 times RT over the pressure of H2, right? Now this pressure here is not the pressure of H2, this is the barometric pressure, right? So what we need is the vapor pressure of water. Now, unfortunately, that is not provided in this question. It should be provided. But what I'm going to do is do a Google search to see what is the vapor pressure of water at 22 degrees. So let me go here. Vapor pressure of water at 22 degrees. Let's see what that gives. 19.8 millimeters mercury, which is the same thing as 19.8 torr. So this should be 19.8 torr. 19.8 torr, right? So in an exam situation, you should be provided that information, right? Now, in order for us to find the pressure of hydrogen, that will be equal to the barometric pressure minus the vapor pressure of water, right? So the barometric pressure is given as 742 torr, which is the same thing, well, not the same thing, minus the vapor pressure of water, which is 19.8 torr. So that will equal to what? 742 minus 19.8. So that gives you 722 torr. 722 torr. So basically, we can now plug everything into this equation. We already have the number of moles, 0.0835 moles of H2 times R, 0.0821 liters atmospheres over mole Kelvin, times the temperature, which is 293 Kelvin, divided by the pressure, which is, we just calculated that, 722 torr, but we have to convert that to atmospheres, right? So 1 atmosphere over 760 torr. And that's it. 0.0835 times 0.0821 times 293, and then divide by 722 divided by 760. And according to my calculation, this works out to be equal to, well, this would have to be rounded up to 3 sig figs, so 2.11, and the units would be liters because the torrs will cancel out here and here, atmospheres cancel out there and there, Kelvin cancels out here, and the mole cancels out there and there. So this would be the answer. All right? You have a question?
Where'd you get the 19.8? Is that the water, is that the?
That's the vapor pressure of the water, that would have to be provided to you. Or at least, if I were to give this in an exam, I would provide that to you, or give you a table. Your tables that have been produced, which gives you different vapor pressure values at different temperatures. Okay, now I think we can, what time is it?
10:30.
Okay, let's see if we can do at least one question, maybe two from the assignment. So we can go back here. Okay, so let me scroll up here. Okay, so we did do, okay, hold on. Oh, the question that I just started to look at, and then, okay, this is the question. So we're going back to this question, which we couldn't do before. The question says there are three containers, A, B, C, and they gave you their volumes, their respective volumes, and their respective pressures of the gases in those containers. And the question is asking, if you were to put all these gases into container B with a different volume, what is the pressure, right? Now, based on this question, we're assuming that the temperature is the same, right? So now that we have covered Dalton's law, right? You know that Dalton's law is one of the equations that you use in order to solve this problem, right? Because basically you just have to add up all the pressures. But the question now becomes, how do you get the pressures, right? And that brings us to the question I have to ask you, what equation comes to mind when it comes to changing pressures and volumes? There is an equation or a law which relates the pressure to volume. And let me give you a hint. It's the very first law that we met. Boyle's law, exactly, right? Boyle's law describes the relationship between the pressure and the volume of a gas, right? So let me see if I can organize it this way. So let me do this for gas in container A. So container A, right? P1 is equal to 3.24 atmospheres, and V1 is equal to 1.23 dm³, right? Now, if you were to put that gas in container B, the volume that would represent V2 would be 1.51 dm³. So my question to you is, how would you calculate P2? How would you calculate the pressure of the gas that was in container A, now in container B? That would be P2. How would you calculate that?
Did you divide the 3.24 atmospheres by the 1.23 and then
Not
multiply?
divide. P1, V1 is equal to P2, V2. That's the equation you're using.
Okay.
So P2, based on this, what is P2 equal to?
P1, V1.
P1, V1 over V2, exactly. So P1 is 3.24 atmospheres times V1, which is 1.23 decimeters cubed, divided by V2, which is 1.51 decimeters cubed. And that would give you the pressure of the gas in container B. So 3.24 times 1.23 divided by 1.51. And according to my calculation, this works out to be equal to 2.64. All right? And the units here would be atmospheres. So that's container A. And basically you do the same thing for container B and C. So for container B, P1 is equal to what? 2.82 atmospheres. B1 is equal to 0.93 dm³. V2 is again the same, 1.51 dm³. So therefore, in this case, P2 will be equal to what? How will you set this up? P2 is equal to what? Remember this? But we're using these numbers now. Oh, this is B2, I'm sorry, this is B2. So P2 is equal to what? 2.82 atmospheres multiplied by 0.93 decimeters cubed divided by 1.51 atmospheres, right? So again, we work this out. 2.82 times 0.93 divided by 1.51. And according to my calculation, this works out. Now this you have to round off to 268, which is 1.7 dm³. No, what am I doing?
Atmosphere.
I did the units wrong. This should be dm³, I'm sorry. So this should be atmosphere. All right, okay. Container C. In that case, in the case of container C, the pressure is 1.21 atmospheres. The volume is 1.42 dm³. And that's V1. P1, and then for container D, 1.51 dm³ again. So what would be P2 in this case? (1.21 atmospheres multiplied by 1.42 dm³ divided by 1.51 dm³. So 1.21 times 1.42 divided by 1.51. And according to my calculation, this works out to be equal to 1.14. Now remember, the question is asking for the total pressure after you put all these gases into container D. So all we have to do is add these numbers here to get an answer. So total pressure is equal to 2.64 atmospheres plus 1.7 atmospheres plus 1.14 atmospheres. So let's see what that gives. 2.64 plus 1.7 plus 1.14. And according to my calculation, now this you have to round off to one decimal place. So the answer becomes 5.5 atmospheres. That would be the final answer. All right. Okay, I think I'm going to stop here. I would suggest, well, before I suggest whatever. Any questions about this? Any questions? Any questions? Okay, so I would suggest, let me, can I clear this? Okay, let me clear this. I would suggest that you attempt on your own question 10, 11, you did 12 already. 10 and 11, all right, those two questions. Also, let me just say by way of announcement, don't come to class next week because there are no classes, right? Next week, you guys will have no classes on Tuesdays, right? On next week Tuesday. Unfortunately, I have to attend some board meetings, so you guys are lucky, I'm not. For the lab class as well. What's that?
Thursday do we have class or no?
We do have class on Thursday, yes. The other thing I want to say by way of announcement, your next test will be week after next. And it will be based on chapters. Chapter 3, 4, and 5. And so all chapters from 3, 4, and this chapter that we're working on, which is 5, which I anticipate we will be finished with by next Thursday. I'm going to make sure that you get back all your graded work before this week is ended. All right, so you'll have that to review. All right, and I think that's all I have to say by way of note. No problem.
So there's merchants, here's seven, and they didn't have anything good there, so. I think last week I-